I am the Philosophical Bachelor, and today I want to be moving towards a philosophy of engineering by considering the question of what is engineering and what makes an engineer an engineer. Any engineer wondering about the nobility of their vocation or in need of inspiration will do well to read civil engineer Samuel C Florman's beautifully written book, The Existential Pleasures of Engineering. Published in 1976, his examples may be somewhat dated, but the ideas and the feelings he conveys remain fresh. It is a book-length ode to engineers, but that is not what I want to focus on. Instead, I want to examine what was added as a postscript in the later edition, a short essay by him entitled The Engineering View, first published in journal The Civilised Engineer in 1987. Because what I am interested in here is not so much the historical evolution of engineering through its technical products or the self-image of an engineer from antiquity to his time, which forms a large part of his book. Instead, I want to consider two more fundamental questions towards a philosophy of engineering. What is engineering and what makes an engineer, which his essay deals with. I will supplement and amplify his message. To avoid tedium, it may not be so clear which are his thoughts and which my additions. But let us just say that I think he will agree with my additions, at least in its broad strokes. Also, one fault with this essay and his essay may be that they deal in generalizations. For instance, Florman says that engineers are hardworking. Since engineers are not all alike and cover a full spectrum of personalities, abilities, and inclinations, all we can describe are tendencies and propensities, or what an ideal engineer will or even should be like. It should be read as such. For those wondering how I am qualified to carry out this analysis, I am an engineer, though I have been out of practice now for decades. I am also a philosopher. I have degrees in both fields. In this essay, I want to look at engineering through a philosopher's eyes. I will bring to bear some of my own views and experiences which form these views. Though science and technology are closely related to engineering is neither. Engineers use science to develop technologies, but their aim is not the same as scientists. Scientists aim to discover theories that describe nature. While scientists are not opposed to the application of their theories, they pursue them not for the sake of their applicability, but for the sake of having a better understanding of nature. Engineers, conversely, are interested in these scientific findings not for their own sake, but for the sake of being able to apply them in order to bring about a concrete product to meet a need. Professor of Engineering David Blockley tells us that the term engineer does not derive from engine, but from the Latin ingenierius, to mean someone who is ingenious in solving practical problems. As for technology, technology is broader in scope than the engineering of technologies. Engineering is one activity towards the development and operation of technologies throughout its life cycle. While the term technology covers the conception and creation of a technological product, which is the domain of engineering, it also covers its use by its end users, which depart from the engineering aspect of the product, among other things. Engineers are not technicians, though engineers may be technologists if they are in the business of creating technologies. Not all engineers create technologies, at least not directly. Technicians have technical skills, for instance in welding, woodworking, building and operating machines, but they do not conceive nor design machines or tools. Engineers may or may not possess those technical skills. Technical skills are not the main focus of our work. In addition to academic qualifications such as accredited degrees in engineering or membership in professional engineering organizations for the engineer, the job scope of an engineer and a technician differs. To preempt any accusations of elitism, I want to make clear that both engineers and technicians are needed to bring about a product. We simply play different roles. Most engineers cannot do what some technicians can do, for instance, welding in underwater environments, while most technicians cannot do what some engineers can do, for instance, developing a design or blueprint for a power plant. Engineer Thomas Treadgold in 1828 gives a definition of engineering. Engineering is the art of directing the great sources of power in nature for the use and convenience of men. It is an art, according to him. Not everything that engineering practice involves can be recorded in words or captured in scientific theories. It involves praxis and a way of thinking developed and refined through experience. It requires an aesthetic sensibility that is yet grounded in practicality. Our designs must be producible, manufacturable using existing tools and machines preferably. If not, we have to design and manufacture those tools and machines that will make our design manufacturable. If after that our design is still not manufacturable, then our design is failed. The raw materials for this production come from nature, such as matter, wood, or silica, though they can also be synthetic, such as plastics. One way to pass the field of engineering is to look at what falls under it. Since there is so much knowledge required, the field of engineering has come to be divided into disciplines, the traditional ones being civil, mechanical, electrical and electronic, and chemical engineering. These disciplines are not all the same age. The first engineers were civil engineers, the term civil distinguishing between civilian building structures as opposed to military ones. As for mechanical engineers, while simple machines were already in use since antiquity, the science behind mechanical machines only came after Isaac Newton in the 17th century. Similarly, while static electricity was observed by Thales around 600 before the Common Era, the ability to harvest, store, and use electricity dates to the 19th century with the first battery by Alejandro Volta, motors by Michael Faraday, lighting by Thomas Edison, and power transmission and radio communication by Nikola Tesla. Likewise for chemical engineering, chemicals were known since ancient times, but the mass manufacture of chemicals in plants will rely on much later developments in chemistry and the other traditional fields of engineering. Within each discipline are further specializations. For example, bridge and tunnel engineering as specializations of civil engineering, power engineering as a specialization of electrical engineering, and automotive engineering as a specialization of mechanical engineering. There are in addition now newer disciplines such as industrial, mining, transport, aeronautical, space, computers, mechatronic, environmental, nuclear, materials, and bioengineering. Then there are the cross-disciplinary fields which I dare not even try to name because engineering work today is often cross-disciplinary. An automotive engineer does not just know the body or engine of a car. Today's cars have many computers on board and electronic suites which control not just the car's informatics and entertainment systems, but also the navigation, power generation, and transmission. This cross-disciplinary need also speaks to why it is important to dispel the myth that engineers work mostly with machines and seldom with people. Due to the demands of complex systems, engineers work in teams comprised of engineers of various disciplines, but also architects, lawyers, business and procurement executives, and marketers. Depending on the products, we may also need the help of medical professionals, chemists, not to mention their customers, including end users. Another way to pass the field is to look at the tasks of the engineering profession. The Committee on the Education and Utilization of the Engineer of the National Research Council in America provides an alternate definition of what engineering is. Business, government, academic, or individual efforts in which knowledge of mathematical and/or natural sciences is employed in research, development, design, manufacturing, systems engineering, or technical operations with the object of creating and/or delivering systems, products, processes, and/or services of a technical nature and content intended for use. In this definition, the tasks are research, development, design, manufacture, systems engineering, operating, creating, and delivering systems, products, processes, and technical services. Florman adds management, teaching, production, inspection, consulting, reporting, statistical work, and computing. The Council's definition begins with the organizations engineers are employed at. They can be businesses, or what we often term collectively as industry today, government, academic, or individual, such as entrepreneurial startups. In addition to technical job roles as engineers, Florman adds consultants, researchers, academics, entrepreneurs, corporate executives, public work officials, civil servants, and programmers who are technical to a greater or lesser extent. There are, of course, engineers that work in non-technical jobs which are not part of the scope of this essay. These lists are in any case not exhaustive, and as it has in the past, will continue to expand since engineering is a profession, but also a fundamental human activity that covers a certain human behavior. What Florman says is an expression of mankind's most basic impulses and most sublime aspirations, which he calls the engineering view. What is that view? While engineering traces back to its roots as a craft involving skills to build and construct, the practice has shifted towards theory, most obviously seen in the way engineers are educated today. Most engineering education begin with a common engineering curriculum, such as mathematics, covering topics such as calculus, matrices, geometry, and trigonometry, physics, such as mechanics, involving vectors and scalars, forces, energy and power, computer programming. These lay a foundation for subsequent more specialized studies, which will continue to include a lot of science and mathematics, for instance, thermodynamics, statistics, fluid and soil mechanics, stress, strain and fracture, and signal analysis. We may also cover material from other engineering disciplines. For instance, mechanical engineers have to study some electronics and materials engineering, since machines today often require an integration of electronic components, and knowledge of materials is invaluable to taking advantage of their mechanical behavior. This theoretical knowledge is based on science, since our task is to apply scientific principles to the design of products. To apply scientific theories implies a belief in science, as contrasted to belief in magic or miracles. This belief is supported by empirical verification, of particular importance to engineers, since our products must be able to function not merely on paper but in real conditions. They must also be safe to use. This stands in contrast to scientific practice. Science, while aiming to be verifiable by experiment, may have experimentation as a later step. Some theories, such as string theory or cosmological theories, may not even be verifiable at all. More interestingly, some scientific theories that are already currently or may in future be overtaken and debunked are still very much in use by engineers, such as Newtonian physics. We are aware that the general theory of relativity and quantum physics are today's leading scientific theories, having outstripped Newtonian physics. But Newtonian physics works well enough for most terrestrial phenomena, and hence we continue to use it. If we are working on the projects involving the very small or on planetary scales for which Newtonian physics may not give correct results, we will switch. Our approach to the choice of scientific theories is pragmatic because we are pragmatic. Engineers believe in truth and are committed to its importance, but truth is not our aim. The main goal has always been to understand the stuff of the universe, to consider problems based on human needs or desires, to propose solutions, to test and select the best solution, and to follow through to a finished product, writes Florman. We want to make a working product and since science helps us get there by describing the physical world, especially in a quantitative way which suits our purposes, we use it. A corollary of this grounding on science is that we put aside our own personal value system. A particular engineer may believe in a certain religion or political ideology, one that he is aware is not universally shared, but that should not factor into his work insofar as he is an engineer. Just because he believes in the importance of reproduction, for instance, should not prevent him from manufacturing a good condom. He is of course a human first and an engineer second. He may express his belief by choosing not to work at a condom manufacturer, but say in furniture design. But should he nonetheless decide to work in condom manufacturing, then he should aim to design and produce high-quality condoms that fulfill their function and are safe for use. He must not, for instance, inject his belief in reproduction into his work and then design condoms that fail, leading to their users' inadvertent pregnancy. Florman believes an engineer should possess clear thinking and be objective, values also compatible with the pursuit of science. He cites mathematician and philosopher Jacob Bronowski, who writes, "Independence and originality, dissent and freedom and tolerance. Such are the first needs of science, and these are the values which, of itself, it demands and forms." Florman thinks that an engineer's virtue lies not in normative ideals, but a commitment to hard facts and a practical bent. An engineer's scientific knowledge and her technical ability help her feel at home in the world. How I understand Florman's meaning here is that because of our understanding of how physical things work and our practical nature, we have a certain confidence that not everyone has. Some people may know how to use an oven or drive a car, but should something go wrong with them, they will have to bring them for repair. Not that I know how to fix an oven or a car myself, but how they work are at least not an insurmountable mystery. Because of my general understanding of technical objects and specific knowledge of machines that I have specialized or had experience in, I will be able to make a first-cut assessment of what went wrong. I will know that machines need maintenance, that they may fail if left unoperated for long periods, that they do not last forever, and if the machine is simple enough, perhaps even figure out how to repair it even if I had never done it before. I will have taken measures to ensure against cases of inadvertent failures, for instance in the case of computers, to back up the hard drive. I will know that I should take some safety measures when attempting to troubleshoot a technical problem, for example switching off the light fixture before attempting to replace its bulb, or wearing goggles when drilling. What I do not know, I am able to find out. That does not mean that I will be able to fix anything. In fact, given the tight integration of many devices today, I will also much of the time need to send them for repair or replace them, since I will lack the tools, the parts, and often the expertise. Yet the terrestrial world is not as big a mystery when we have, and know we have, the capability to understand how things work and be able to extrapolate from what we know to what we do not know, and have a deserved confidence to know that we are probably right. When we are wrong, we have an ability to learn what then is right and to incorporate that information into our body of knowledge. In Florman's words, we do not feel alienated, as some people say they do, by the scientific advances of our age. For myself, I think this ability comes from my innate curiosity about how things work. These things may be machines like fans or calculators, but also can be the economy or society, and in some cases, I may be motivated to find out. Are you the kind of person who walks up to an automatic door which opens and wonder, how did it know I was coming? And when you find out, be it by searching the web, reading about it in a book, or asking around, you actually feel impressed, amazed at how brilliant the idea is. Motivation alone is of course not sufficient, though it serves as a good starting point. Hard work is also required, according to Florman, though I think that an innate curiosity can be a motivator to do the hard work. He elaborates, Knowledge and understanding are precious objectives worth striving for. The quest for excellence is a virtuous enterprise that needs no rationalizing. I think he says this because the knowledge and understanding he has gained has helped him do things he is interested in. He is thus motivated to acquire knowledge and understanding. I suspect that if he was made to simply have knowledge for its own sake, like to memorize 10,000 digits of pi or a phone book, that he may become exasperated. Digging a hole in the ground and then filling it up is hard work, made especially hard because it is futile. Digging a hole so that one can bury some treasure remains hard work, but you know at least why you're doing it. Yet, scientific truths and theories are not enough when it comes to the real world. In the real world, we deal not with theoretical forces and ideal substances, but with impure materials and non-laboratory conditions that may behave in non-ideal and hence unpredictable ways. We have to use such real materials in real conditions to create working products, to perform desired functions under real constraints of time and money. Not only are engineers not in search of absolute scientific truth, we are not in the business of creating perfect products, since perfection will take an inordinately long time to be obtained and cost a lot. Good enough is what we have to settle for, not because we like it that way, but because our clients do not want to wait a long time or pay a lot. This satisficing approach means that there remains some risk of failure. Engineers face two conflicting demands. Humanity wants to do more and go further. They rely on us to span ever-widening chasms, build taller buildings and broader domes, create more sophisticated machines, and tap ever more elusive forms of energy. We want to do all that while minimizing risks, eliminating them if possible, and be prudent in our work. However, even when we manage to successfully avoid known errors and problems, there is still a remainder of unknown problems that can arise. Besides, even known problems can still arise since their probability of arising may be reduced, but over the long haul, the improbable becomes the inevitable, and accidents will happen. In addition, as Florman tells us, not that it is difficult to design redundant safety features into a product, it is merely expensive. Engineers can build airplanes as strong as tanks with thick walls and plenty of safety equipment such as airbags and parachutes, but then they will have less capacity for passengers and cargo and consume more fuel. We often cannot have our cake and eat it. The degree of compromise is decided by regulators, business, and consumer preferences, while engineers have to deliver in the face of these conflicting demands and take responsibility for their work. Besides, the state of the art is not complete. Matter fatigue, for instance, is still not completely understood, and hence we are unable to predict when it will fail, especially when subject to vibrations and erratic stresses in changeable climatic conditions and over long periods of time. Unfortunately, failure sometimes has to be our teacher, but we also must have the tenacity and courage to learn its lessons in addition to accepting responsibility. Earlier, I gave an example of how an engineer's work at a condom manufacturer may conflict with his personal values favoring reproduction. He may certainly decline to provide his services to such companies, but if he accepts to provide them, then he is obliged to provide them to the best of his abilities, putting aside his personal views and mores. Engineers should not be the judge of what is good or suitable for society. The products of our work are often not decided by us, but by the companies we work for, which in turn are responding to the demands put to them by the market, which is a proxy for society. Florman writes, I do not believe that it is up to the engineering profession to decide what is good for society, to decide, for example, whether we should favor mass transit or individual automobiles, allow drilling for oil off our coasts, authorize the use of public lands for mining, or determine how much of our national product should be devoted to armaments. In other words, I do not believe in technocracy. Instead, he espouses a democratic ideal, where the goals are decided collectively by society, be it through the marketplace or the ballot box. In the pursuit of goals established by the entire community, engineers should be dependable, he says. This commitment to dependability is not unique to engineering, but is the essence of professionalism across all professions. A lawyer does not support a client's criminal actions, but is nonetheless duty-bound to provide the best defense. A doctor may not agree with her patient's sexual promiscuity, but is obliged to provide her treatment. We could decide not to provide specific services or to select our clients or employers, but if we do accept to work for them, then we must carry out our work dependably and professionally. Engineers, in turn, depend on society to function effectively in order to effectively carry out our work. If there is no law and order or reliable power supply from the state, then the output of our manufacturing machines are impeded due to a lack of raw materials or electricity. We often work in large organizations and carry out large projects. We rely on others to also do their work well and have to cooperate with them to do our work well. That does not, however, mean that all engineers are lackeys of capitalism. Engineers work in many settings. Most are in industry where their corporations respond to the demands of the marketplace, but we also work in government to oversee public infrastructure and participate in regulatory functions. We are found in academia, educating future generations of engineers. We provide consultancy services to industry, but also to public interest or non-profit organizations. We serve our organizations, but in that service, we also serve society. Florman thinks that engineers are no more altruistic than the average citizen, but by being hardworking, responsible, dependable, and creative, we end up being of service to the community as well as enhancing our own pride and pleasure. It is an enlightened self-interest. He believes that the contribution by engineers to technological progress further culture, democracy, and human progress. The inks and brushes devised by engineers make painting possible. The development of mass media technologies such as the printing press, radio, and television by engineers facilitate the spread of ideas, furthering education and bringing culture to the masses. Better agricultural tools and methods lead to better yields, which reduce global poverty and hunger. Unfortunately, not all technological change is beneficial. Engineers are excited at the prospect of new discoveries and ever-receding horizons, though we are chastened also by the potential harm that may result. Engineering is a serious and methodical endeavor involving logic and precision. It requires serious engineers. Yet it is also fun and creative, requiring leaps of imagination as well as painstaking care. Florman summarizes, "These are what I take to be the main elements of the engineering view. 1. A commitment to science and to the values that science demands: independence and originality, dissent and freedom and tolerance. 2. A comfortable familiarity with the forces that prevail in the physical universe. 3. A belief in hard work, not for its own sake, but in the quest for knowledge and understanding and in the pursuit of excellence. 4. A willingness to forego perfection, recognizing that we have to get real and useful products out the door. 5. A willingness to accept responsibility and risk failure. 6. A resolve to be dependable. 7. A commitment to social order along with a strong affinity for democracy. 8. A seriousness that we hope will not become glumness. 9. A passion for creativity, a compulsion to tinker, and a zest for change." I want to round off this essay by considering what he meant by existential in the title of his book, The Existential Pleasures of Engineering. Existentialism is a philosophical movement made popular by thinkers such as Jean-Paul Sartre, Simone de Beauvoir, and Albert Camus post-World War II, alongside earlier thinkers like Soren Kierkegaard and Friedrich Nietzsche. It is called existentialism because, as Sartre writes, existence precedes essence. We are not born fully formed into what we are to be. We were first born and only later become who we are. We invent who we are. There is no fixed mode for us to be shaped into. When we are authentic to ourselves, we come into our being by working out our own personal meaning to our existence. Relating this back to Florman's book, one reason that an engineer derives pleasure and fulfillment from his engineering work is because he finds meaning in that work. Not everyone enjoys tinkering with machines, creating technical designs, bearing the rigors of detailed calculations, simulations, prototype development, design reviews, and then full-scale manufacturing, repair, maintenance, and product retirement. Not everyone has the ability to do so either. Most leave it to others to do the technical work. They only wish to utilize the end product. Do you live in a house or a building and wished you built it? Do you use your computer, phone, television, air conditioning, or car, or take the train, bus, or plane, and wished you had a part to play to produce them? I suspect most will not, and that is good and well. We are not all suited to be engineers, just like we are not all suited to be accountants, lawyers, doctors, or philosophers. It is not that engineers are in a state of perpetual bliss while working. We can expect to suffer strain, be anxious, worried, troubled, and face reprimand over our work. But we can also enjoy the satisfaction of a job well done, not just at the end when the product is delivered, but also during the process, even amid the strain and tension. We bring our engineering ability to our projects, and in our work, we satisfy our primal desire to build, to create, to engineer. That is the source of the existential pleasure of an engineer. In our engineering work, we are who we want to be. Thank you for listening to the Philosophical Bachelor.